recorded now. Okay, there we go. So it's being recorded. Okay, so solutions of sodium monohydrogen phosphate. So I'm pretty sure we already did the inventory for this. So I'm going to go ahead and write the inventory, which we had sodium ions and monohydrogen phosphate. Unless, did we finish this whole one? Monohydrogen phosphate. Yeah, I think we did finish this one. Oh, it's looking familiar. Okay. Yeah. So let's move on to the next one. Solid sodium amide is mixed with water. Okay, so I'm going to clear that. Now, amide is on the list that I gave you for bases. And amide this is a strong base. And the formula for amide is NH2 minus. And so what are the strong bases? I know I'm having you memorize the 7 common strong acids. I'm not necessarily having you memorize the strong bases, but let me just write them over here. The strong bases that you should be familiar with are going to be the soluble hydroxides. The soluble hydroxides are the group 1, ammonium, calcium, strontium, barium. Soluble hydroxides. These are the group 1, ammonium, calcium, strontium, and barium. And so the soluble hydroxides are considered strong bases. The base part is the hydroxide ion. The sodium ions, ammonium is actually an acid. Calcium, strontium, barium, those are all neutral. Sodium, lithium, potassium, all neutral, except for ammonium, which is a weak acid. And so even though it's ammonium hydroxide, you might think ammonium hydroxide has got a weak acid, but it has a strong base. And so the base properties dominate usually. And ammonium hydroxide is not stable, you know. Ammonium hydroxide is unstable. If you take an acid and a base and try to put them together, especially a strong base like this, they'll want to react with one another. And when they react with one another, they'll try to form weaker acids and weaker bases in the process. So this is one of the reasons ammonium hydroxide is not so stable. But ammonium hydroxide would be a strong base because it's a soluble, hydroxide. Insoluble hydroxides are not considered strong bases. So you might have something like iron 3 hydroxide, and iron 3 hydroxide, even though it has lots of hydroxide, if you look at iron 3 hydroxide, there are 3 hydroxides for every iron. And so you would think it's a strong base, but it's not very soluble at all. And so the soluble hydroxides are strong bases, but there are others. The others would be like soluble oxides. The oxides are O2 minus. And so things like an example would be like the group 1, oxides are soluble, like sodium oxide, Group 1 ammonium. However, calcium, strontium, barium oxide are insoluble, So it's just pretty much group 1. And ammonium oxide, it doesn't exist, I don't think. Oxide's too powerful of a base to not react with ammonium. And so basically the group 1 here. This is not on the solubility rules that I told you, oxides, but we know most oxides are insoluble, like rust and that type of thing. And so this is just based on observations. The amides, would be like this one, sodium amide. Group 1's also soluble. Amides are typically, these are soluble. There aren't that many amides out there, And this is an example of one amide. It's a strong base. And then, just 1 second. Okay, I'm back. Sorry about that. This is something's wrong with my computer. A lot of clicks, but so amide is not, it's not that common. So a lot of people don't know what amide is. There are other strong bases like hydrides. Hydrides are strong bases. These are H minus, it's just hydride. And methide is so rare. Even though methide's on the chart, these are much more common. The most common are the hydroxides, and then some soluble oxides, you'll run into. Insoluble oxides are not, like rust, iron 3 oxide, Fe2O3. It's not a strong base. But it is basic, rust. Could potentially react, little. Amides, hydrides, these are all more common. So what we have is the sodium amide. Sodium is a +1, amide is a -1. So the formula for sodium amide is just NaNH2. And sodium amide is mixed with water. So there's also water present. And so what kind of reaction are we going to have here? And so if you recognize that amide is a strong base, then, Bronsted acid-base reaction is probably a good candidate. And so let's try Bronsted acid-base reaction in this particular case. Sometimes people do a double replacement. Sometimes people might do a double replacement considering H2O as an HOH. And so this could be an ABCD type deal, or you just do the Bronsted method. In the Bronsted method, it depends on how reactive, these species are. In the Bronsted, it's probably best to do just the Bronsted. It's going to be sodium ions are present, amide ions are present, water is present. So that's what we got. And sodium ions are neutral, those don't occur. And so I use capital N here for neutral like I was doing before, but I didn't really explain it. Neutral means it's not on the chart, and it's not really going to be on the chart because Na doesn't have any H. Acids have H, the element H. And Na really doesn't want an H plus, an Na plus and an H plus don't really like each other. Basically, they're both the same charge. Sometimes you have the same charge species react, but they're positive atoms in a negative ion, let's say, that might react. And going over here, amide we know is a base, it's a strong base. Water is both an acid and a base, so we have very little choice here. The acid's got to be water here. Now we have a choice. The base could be water or amide. Which one's stronger? Well, amide's stronger. Sometimes the strongest species is the same species. If the strongest species is the same species, that can happen. And we have what's called autoreaction. That is, one of them acts one way and the other acts the other way. It's like mercury 2. You could have two mercury 2 ions react together, and one of the mercury 2s acts as the, or actually mercury 1, sorry. You have two mercury 1s react with one another. One of the mercury 1s acts as the oxidizer, the other acts as the reducer, and they can react. And this is the same thing. It could potentially be, if there's nothing else around, then water could be both the acid and the base. That's called auto hydrolysis or auto ionization or auto reaction. Auto means self, we're just reacting with itself. In fact, that self reaction is very important in pH. It's not very favorable because of the products, but it's, it's critical. And this is why, water has, pure water has a pH of 7. We'll talk about pH later. Okay, then we have amide here, but amide's much more powerful, so that's going to be the base. And when we do this, we'll just take the acid. The acid's going to lose a hydrogen ion, and the base is going to gain that hydrogen ion. And so what will happen here is this will lose an H plus. If it loses an H plus, we're going to be left with an OH minus or hydroxide. And this one's going to gain an H plus. If it gains an H plus, then we'll be left with NH3. So we're going to form hydroxide and ammonia. Okay, then we look, this is the acid and this is the base. And what we do in chemical reactions is we look for the competing reverse reaction. You know, which way is downhill? Is going forward downhill or is going backwards downhill? And so going downhill, now this is tricky because if you look at the chart, hydroxide is normally thought of as a base and ammonia is normally thought of as a base. So which one of these is the base? You know, which one's the acid? Actually, hydroxide's amphoteric, but you know, normally it's thought of as a strong base because it is a strong base, but an exceptionally weak acid. And ammonia is thought of as a weak base, and it's an even weaker acid. And so what we're looking at here is going backwards. We have to visualize, is hydroxide gaining H or losing an H? And so if we go backwards here, hydroxide goes backwards to water. And so it's gaining an H. If it's gaining an H, then that's called a base. You know, bases are proton acceptors, H plus acceptors. And acids are what we call proton donors or H plus donors. And so, so this is accepting a proton. Well, who's losing the proton? Ammonia is losing a proton. So normally ammonia is thought of as a base. But in this reaction, it has to be the acid. And then we compare which base is stronger, amide or hydroxide, and which acid is stronger, water or ammonia. And so here we can consult the acid-base chart. Let me just see, it's going to be complicated because I'm just working on one screen. Okay. So let me share that here. Okay. Fortunately, I have it closed. Well, do you have your acid-base chart handy? Take a look at the acid-base chart, and why don't you tell me which one's stronger? Which one's a stronger acid, water or ammonia? The acid-base chart I posted on Piazza. Ammonia is a stronger acid? You have to be careful because the acids are on the left side. The bases are on the right side. So make sure you're looking on the left side and then determine which one's the strongest. Yeah, that's correct. Water is a stronger acid. Make sure that you see that. Water is a stronger acid. Ammonia is a weaker acid. Okay, now look at the base. Compare amide, NH2 minus, with hydroxide. Which one's stronger, amide or hydroxide? Yeah, amide is stronger. It's always got to go this pattern, strong, strong to weak, weak, or weak, weak to strong, strong. It can never go strong, weak. If it does, then made a mistake. And so if we're going strong to weak, it's downhill in the forward direction. Forward direction is downhill. Reverse direction is uphill. So I'll try to draw a big arrow for forward and a tiny arrow for reverse, you know. This is what we call the driving force here. And so that's another example of a Bronsted acid-base reaction. Now, we're going to talk about structure and acidity. Let me clear these, John. We're going to talk about structure and acidity later when we get to Lewis structures. Talk some about the theory. Then we're going to talk about Lewis acid-base reactions later. Here. We'll do an example, a couple of examples of Lewis acid-base reactions. This is just an intro. We're going to come back to acids, so I'm not going to go into it in that much depth. Just we're looking at chemical reactions. And acids are going to have H, the ones that we're going to deal with. We aren't going to get into more complex. There are more complex Lewis acids. More complex Lewis acids would be like carbon dioxide. Carbon dioxide is also an acid, but how do you recognize it as an acid? You know, when you look at CO2, this is an acid. But this doesn't fit the other definition. You know, Bronsted said acids are proton donors. There's no hydrogen here to donate. There's no hydrogen atoms. So how can it be an acid? Well, it's not a Bronsted acid. This is what we call a Lewis acid. Lewis acids, all Bronsted acids and all Arrhenius acids are also Lewis acids. Lewis acids is the all-encompassing definition of what an acid is. If we look at the universe of acids, then Lewis has them all covered. The Lewis definition covers the entire universe of acids. The Arrhenius acids is just a little corner here. And so if we're looking at Arrhenius acids, we're just looking at a little corner of the universe, Arrhenius. If we're looking at, Arrhenius is 1R, I guess, not 2R, I think. If we're looking at Bronsted, then Bronsted is a bigger chunk of the universe, but we're still not looking at the whole universe. You know, the Bronsted acids fill up this much of the universe. If we want the whole universe of acids, then we have to use Lewis. We have to look at it through the Lewis lens. Because if we look at it as the Bronsted, we're just focusing on a small part of the, well, not a small, it's a big chunk of the universe here. If we're looking at the Arrhenius lens, we're only looking at a tiny part of the acids universe. But the reason we look at this smaller part here is because the rules for Bronsted are pretty straightforward. You know, the rules for Lewis are a bit more complex. And, also identifying Lewis acids is a bit more complex, like CO2, you know. How do you know? You could do it experimentally. If you, for example, if you took a straw and bubbled air bubbles through water, you're going to make the water more acidic, and you can actually measure the change in the pH by exhaling CO2, you know, exhaled breath through water. And so, you know, there are ways to determine it experimentally, but we want to determine it theoretically, more theoretically. You know, we don't want to have to mix everything with water to see what it does to the pH, you know, of the water. pH, you know, as pH goes down, it becomes more acidic. As pH goes up, it becomes more what we call basic. And there are other ways of telling acids. Acids are usually sour, like citric acid in fruit, you know, vitamin C, those types of things. They're more sour. Whereas bases are bitter, like soap. You know, soap is pretty basic. Detergents, that kind of stuff. So anyway, that's what's helpful about learning more structural theory. So we don't have to experimentally determine what the compound does to pH. Ammonia will increase the pH, you know, of water. All right. Now, let me end this here. We're going to start the, oh, I didn't want to do that. We're going to start the next chapter, actually, but we really aren't done with this because we're going to do a lot of examples. In lab, we're going to do a whole bunch of chemical reactions, so we'll get more practice there. And as we go along, you know, we'll get more and more practice, including in the next chapter, which is chapter 10 here. And so let me share this here. And so we're going to start chapter 10, but I think it's break time, so we do that. We just go slideshow, current slide. Make sure you guys see that. Let's go there. Okay. So let's go ahead and take a break. We'll take a 15-minute break. Oh, is it in 30 minutes? Oh, you're right. It's in 30 minutes. Sorry. What am I thinking? It's 12. No wonder I was thinking, man, I'm pretty slow today, but I was having technical difficulties. So yeah, 30 more minutes. We'll do break time every hour. All right, let's take a look at chapter 10 now then. Chapter 10 deals with stoichiometry. So first off, what is stoichiometry? And so stoichiometry, there are lots of different ways you can define stoichiometry, but you know, the chapter is not titled stoichiometry. The chapter is titled quantity relationships. And so stoichiometry, what that is it's just quantity relationships. We've already been doing quantity relationships. For example, H2O, you know, 2 hydrogens for every oxygen. That's stoichiometry. You know, H2O has 2 hydrogens, 2 oxygens, 2 hydrogen atoms, 1 oxygen. I mean, or you could say 2 dozen hydrogens, 1 dozen oxygen. Or you could say 2 moles of hydrogen atoms, 1 mole of oxygen atoms, a mole being 6.022 times 10 to the 23rd, you know, units or atoms. And so that would be the same thing. Just 1 second. Okay. All right. All right, I'm back. So let's take a look at other quantity relationships. There are also quantity relationships in chemical reactions. Like, you know, when we have methane needs, each methane molecule needs 2 oxygens. If I don't have 2 oxygen molecules, then I might get carbon monoxide, or I might get soot instead if there's not enough oxygen, you know. And so those types of things are the quantity relationships. And in stoichiometry, we're looking at the ideal, you know, ideal quantities that we need. These ideal quantities I call theoretical. Your book is going to call them ideal, I think. Let's take a look at this example here. You know, chlorine. Chlorine is very reactive. Chlorine is the most produced inorganic chemical in the world. And there's no mines, you know, there's no natural chlorine. All the chlorine in nature is chloride, because chlorine's too reactive, it's unstable. So chlorine's like the, you know, the Mr. Hyde of the Dr. Jekyll and Mr. Hyde. It's very unstable and reactive chemical. And so chlorine has to be made, you know, and we make it from chloride, which is a heck of a lot more stable. And so it is usually manufactured in large industrial plants by subjecting salt water solution to an electric current. Electric current, that's called electrolysis. And the reason is there's no driving force. This reaction is totally uphill, yielding chlorine, hydrogen, and a solution of sodium hydroxide. So this is a redox reaction here. And sodium chloride is very stable. Water is very stable. Actually, if there's water present, this should just be NaClAq, you know. And so when you mix salt with water, it's stable. I don't usually put a gap here. You know, they put a gap here. I don't usually put a gap here, but I usually put a gap here. That depends on the style. You know, there's style guides, scientific style guides. And some people don't put gaps on either end to save space, you know. These style guides, they're very strictly adhered to for scientific publications. Like if you put a gap there and a gap's not allowed, your paper is rejected. They won't accept it. Or if you don't have a gap here and there's supposed to be a gap, then it's rejected. And so those are all style issues. Most people don't put a gap here. And so this is very unusual to have a gap here. And here it's kind of, you see it both ways. There's either a gap or there's no gap. Okay. Well, anyway, if we have solid sodium chloride in water, sodium chloride is highly soluble, so it should be NaClAQ. And when NaClAQ is electrolyzed, well, water is going to participate in this reaction here. We're going to form chlorine and hydrogen. The reason why water participates in here is because we really should form sodium metal. In this case, the sodium that's generated through the electrolysis of the salt reacts with the water to produce hydrogen instead and sodium hydroxide. I guess, you know, both of these are very useful industrial chemicals, chlorine and hydrogen. And so this is a redox reaction, you know. We could have figured this one out as well. You know, if I wanted to figure out the redox here, let me just do that as a quick example, since we can always use more practice for this. I would have said, okay, what kind of redox can we have for sodium chloride AQ? And the way we use this is the chart method. And so let's look at potential redox. I don't know if there's a driving force until after predicting the products. So what we do is we first predict what the most likely products are, and then we determine driving force. And so this is why it's potential. It's not going to happen unless we have a driving force at the end. But the chart method works nonetheless. So what we have present is we have sodium ions, chloride ions, and water. Now this is a different chart. This is not the acid-base chart. In the acid-base chart, we said sodium ions are neutral. But in the redox chart, which is to the left, what are sodium ions? Are sodium ions on the left side of that chart, on the right side of the chart, or on both sides of the chart? Can you tell me? What side are sodium ions? Left side, right side, or both sides of the chart? We always have to be aware that things can occur on both sides of the chart. Sometimes when we look at it and we find the first entry, then we just stop there and don't look any further. But here we have to. Yeah, it's on the left side. Is that the fluorine side or the lithium side? Fluorine being F2. Is that the F2 side or the Li solid side? That's the next step, because sometimes the charts are inverted. You know, it used to be in the old days, all the charts looked like the activity series. That is, they put all the reducing agents on the left side, all the oxidizing agents on the right side. And then around 1980s or something, they switched, I think. Maybe it was I think it was around in the 1980s, it was switched. And so they put all the oxidizing agents on the left side and all the reducing agents on the right side. So if you use an old table, you'll see, hey, this old table's upside down, you know. It's gonna look like it's upside down if you're used to the table in our book. And the one I gave you as a handout. And so, you know, don't use left and right. Use, you know, fluorine and lithium. Fluorine and lithium are the way you can tell if you're upside down or right side up, you know. It's like being in zero gravity. We know which way is up or which way is down. How do you know? You know, you need some kind of reference point. You know, the reference point might be Earth, you know, something like that. So it's on the fluorine side. So this we call an oxidizer. You know, oxidizing agent, OA, oxidizing agent. How about chloride? Chloride on the lithium side or the fluorine side, or both? No, lithium metal side. Kazar, the fluorine side, or check that again. You know, it's chloride, not chlorine. Chlorine is on the fluorine side, but chloride is on the lithium side. And so if it's on the lithium side, it's a reducing agent. It only occurs on one side, you know. And so we have to distinguish between chlorine, which is highly reactive, and chloride, which is quite stable. And then water. How about water? What side is that on? Yeah, water is both. So it's both. It can go either way. It's an oxidizing agent and a reducing agent, either way. Same thing in acid. You know, acid base, water can go both directions. And water, interestingly, as an acid or a base, either direction, it can go with equal ease. However, in redox, sometimes that doesn't happen. You know, one way's better than the other, but both of these are weak. So even though they might not be equivalent, they're extremely, water is not a very good oxidizer, nor is it a very good reducer. An oxidizer would support combustion, you know, a reducer would be the fuel for combustion. So anyway, then we're going to look, okay, what is the strongest oxidizer present? So we have a choice between sodium ions and water. What is a better oxidizer? Sodium ions or water? Take a look at the chart. I would bring up the chart, but it'll take me like a few minutes to bring up the chart because I'm only on one screen today. So tell me which oxidizer is better or stronger, sodium ions or water? Okay, that's correct. It turns out water, does everybody see this? This one always throws people off. So many people will tell me sodium ions are stronger. And the reason is water's mispositioned. You know, water's at the very, very bottom of the chart, but it doesn't belong at the bottom of the chart. Where does water belong? Water belongs between zinc ions, Zn2+, and aluminum 3+ ions. That's where water belongs. Okay, now let's take a look at the reducing agents. Which one is a stronger reducing agent? And it could very well be that water is the strongest oxidizing agent and the strongest reducing agent. That would be auto reaction. Auto being self-reaction. That could very well be. But let's see, in this particular case, is chloride the better reducing agent or is water the better reducing agent? You tell me. So look at the chart. You're on the lithium end, you know, the lithium side. So look at the chart and tell me which one is the better, is the reducing agent. Okay, chloride is Cl minus, not Cl2 minus. So be careful with that. It's Cl minus, and we have two of them. So chloride, does it, it doesn't matter if there's a 2. The 2 is just to balance things out. I completely ignore the 2. You know, it's just chloride. That's just to tell you the ratio that it does. So the 2 is not really, you know, the numbers here, like, you know, 2, I don't really pay attention to those. Those I do at the end, you know. Here we're just looking at reactivity. And so whether it's two Cl minuses, 1 Cl minus, 3 Cl minus, it doesn't matter, it's Cl minus, and that's where it's ranked. Okay, does everybody agree that Cl minus is a better reducer than water? Okay, yes. Yes. Okay, let me take a look at this chart here. I'm gonna just take a moment. I have to stop the share, or let me pause the share here. I need to open up the Okay, let's take a look at a chart here, and we're looking at water versus chloride. And so, yeah, I need to zoom in here. So I see chloride here, right here. Okay, and then the problem is I see two waters. You know, I see this water, but there's oxygen. We don't have oxygen, so I can't use this. But I do see this water here. You know, because we don't need to have air in this reaction. They didn't say if it's being done in space or wherever. This water requires manganese 2. This water requires lead 2. None of those present. This water requires chromium 3. This water requires manganese 2. But this water does not require anything. And so I have two waters. Which of these two do I pick? Well, if I have two waters there, I have to pick the stronger. And so which one of these is stronger? Well, the stronger one's the one that's closer to lithium. So lithium is the strongest reducer. So if I look at where lithium is positioned down here. There's lithium. That's a strong guest. Let me go back up here. And so that means I ignore this one, you know, because the strongest are the ones that are going to react. And so I have to go with this one. This is the water I must go with. Well, if that's the case, if this is the water I must go with, then which one's stronger, chloride or water? Which one is stronger? Yeah. Water is. Water is a stronger reducer. And so you have to do that. Okay, this brings up the exception here. And this is the only exception you need to know. Remember, sometimes there are exceptions you need to know. Of course, you know, in nature, you know, the strongest are going to want to react, you know, but sometimes certain things happen, you know, in nature in terms of energetics. Let's say you want a big return on some investment. You want a big return on some investment, but you have to invest a lot of money into it. And so you got to commit a lot of money, but you're going to get a big return. But you can get a decent return by committing minimal money. And so sometimes you'll go, you know, I don't want to invest this much money for a bigger return. I'd rather invest minimal money and get a decent return quickly, you know? And the big return is going to take more effort, more time to get. And so sometimes, you know, if one thing costs you very little effort, but you don't get as much return, it might be better. And so this is what happens with chloride. Chloride is easier to oxidize, but you get less return. Chloride is easier to oxidize because all you're doing is you're plucking an electron, you know, off this atom. And so if you're an oxidizer, you know, an OA is going to come over here and just kind of pluck this electron, you know, off the atom. That's it. But if you're water, what you have to do is take a look at what happens with water. When electrons are plucked off water, everything gets rearranged. You know, the oxygens have to rearrange to form O2, and then the hydrogens are all completely plucked off. And so when we pluck it off water, there's a lot more energy invested in breaking apart the water molecules. We have to completely break apart the water molecules. The water molecules are usually drawn like this with 4 dots up here. And that's a lot of work, you know, plucking off all the hydrogens and rearranging all the atoms, and we're oxidizing the oxygens. The oxygens are -2 here. The hydrogens are +1. So we're oxidizing the oxygens, stripping the electrons off that, you know, it's a lot of work. And so what happens in nature is, this is something that's called kinetics versus thermodynamics. Kinetics is, this is going to happen quickly. You know, oxidizing agent is going to come along here and pluck the electron off. It's simple, easy job. You know, quick, simple, easy job. Over here, it's a much more complicated job. You know, it's got to pluck off the electrons off the oxygen. The oxygens have to combine, and the hydrogens are left alone, no electrons. And so this one is going to yield you more return, return being energy, more stability. So this one's going to be more downhill. And so the other thing is like this, you know, if it were all downhill, then there's no problem. And so let's say you want to go down a slide, and there's a small slide you can go down, and it's like this, and you don't have to climb that many steps up to have a nice trip down, you know, the slide. And then there's a much larger slide, but there's a huge hill you have to climb up in order to go down the slide, but the slide is a lot longer, you know, and so it's more downhill, a lot longer from where you start here. That's where you start to where you end here. You know, it's a lot longer than here, let's say, although I didn't really draw it. But there's this huge hill you have to climb in order to go down this longer slide. Well, that's what's happening here. There's this huge hill you have to climb in order to react with water, but the return is much better. That is, you're going to go downhill more, you know, and what we want to do is we want to go downhill in these reactions. But this one, hey, you go downhill about, you know, not that big of a difference. It's not that huge of a difference, you know, between chloride and water. And so not that huge of a difference for a lot less work. You know, if you look at the numbers here, this is 1.358, this is 1.229. It's not a huge difference for a lot less work. And so this is why this is an exception. We would predict water to be the better reducing agent, but it turns out when it's water versus chloride, chloride wins because of something called kinetics versus thermodynamics. Thermodynamics is just energetics, looking at it here. Kinetics is looking how big the hill you have to climb. That's kinetics. Thermodynamics is looking at where you start and where you end, not how big of a hill you had to climb to get there. You don't have to worry about kinetics and thermodynamics just yet. We'll talk about that later, probably. And so this is the only exception here. And so this goes against what we would have predicted. I would have predicted that water is, oh, did I lose my drawings? Yes, I did. Okay. That's not a problem. All right, so here, I'm just gonna draw it in red here. Sodium ions, and we had chloride ions, and we had water. And so we're looking at reducing agents here, you know, chloride and water as reducing agents versus chloride versus water. Water should win, according to chart, water should win. According to chart, H2O should win. But chloride wins because of kinetics. we talked about kinetic molecular theory. It's all kind of related earlier. So unexpectedly, this is only one exception. Only exception you need to know. Only exception you should know. And so unexpectedly, we're going to go with chloride. And so that means the OA is water, oxidizing agent is water, and the reducing agent will be chloride. So we'll just copy down the half reactions off the chart. And so I think I need to clear these annotations. So let's see how I'm going to do that. Okay. So we'll write down the half reactions. So when chloride acts as a reducing agent, 2 chlorides go to a chlorine plus 2 electrons. When water acts as the oxidizing agent, then we're going to have 2 waters goes to, 2 waters, actually oxidizing agent, sorry. When water acts as the oxidizing agent here, the H's are picking up the electrons. H is +1, O is -2. And so it's going to be 2 H2O's plus 4 electrons yields H2 gas plus 2 hydroxides. I just copied that off the chart here. Okay. Did I screw that up? Yeah, I did, sorry. Plus 2 electrons. The chart might have this doubled. I'm not sure. But this is what I have. All right, so this one produces 2 electrons. This one consumes 2 electrons. So I don't have to multiply these by any factor. And so let's get the net reaction here. Net reaction is going to be 2 chlorides plus 2 waters plus 2 electrons yields chlorine plus hydrogen, plus 2 electrons, plus 2 electrons plus hydrogen plus 2 hydroxides. And so here the 2 electrons cancel, and we're going to be left with 2 chlorides plus 2 waters yields chlorine plus hydrogen plus 2 hydroxides. That's what we're going to be left with. Now let's put in the states here. States for chloride will be AQ. H2O would be a liquid. Chlorine would be a gas. Hydrogen would be a gas. And hydroxide would be AQ. Now the chart method always yields the NIE. Ultimately when we use the chart method, gives the NIE. And so this is the NIE we're left with here. They didn't do, this is the CE here that they did. And so let's see what's going on with that. So I'm going to erase this here. Sorry. Don't have that much room. So if we if we look at their equation here, then I'm going to get the IE for this. And so IE, we ionize or dissociate the strong electrolytes. So for example, sodium chloride. Sodium chloride is a soluble salt. Soluble salts are strong electrolytes. And so we dissociate it. So if I have two NaCl's, I'm going to call this NaClAQ, you know, or because there's water around. And if there's water around, this is going to dissolve. So it's going to break up into two Na plus AQ. Like I said, I'm going to call this AQ because if you mix these two, the salt will dissolve again. And when the salt dissolves, you know, it breaks up into ions, 2 sodiums and 2 chlorides for every 2 sodium chlorides. This will be AQ. Water is not a soluble salt, it's not a strong acid, and it's not a strong base, so we don't do anything, we just leave it alone. Chlorine is not a strong acid, not a strong base, and not a soluble salt, so leave it alone. Same thing with hydrogen, leave it alone. Sodium hydroxide, however, is a soluble salt. All group 1 salts are soluble. You know, the hydroxide itself is a strong base. So I call this, you know, sodium salts are all soluble, so I just call it sodium salt. That's going to lead to 2 sodiums and 2 hydroxides. Okay, what are the spectators here? Well, the sodiums don't seem to be doing anything. Chloride did because it went from chloride to chlorine. Water did, for sure, because water went from water to hydrogen gas and hydroxide. And so it looks like the sodium ions are spectators in this particular reaction. And so when I do the NIE, I'm going to get 2 chlorides plus 2 waters yields chlorine plus hydrogen plus 2 hydroxides, which is the same, you know, the same. And so we could have predicted this. You know, the problem is there's no driving force for this. And so when we look at the driving force, okay, what was chloride? Chloride is the reducing agent. Water is the oxidizing agent that's going in the forward direction. Going in the opposite, I shouldn't erase my half reactions, but chlorine is the oxidizing agent if we went backwards. And hydrogen and hydroxide would be the reducing agent going backwards. And so we got to figure out which way is downhill, you know, forward or backward. And so when we compare it should be easy, but I don't think we need the chart for this. What is a better oxidizer, water or chlorine? You know, this one should be self-evident based on your experience, you know, based on your memorized knowledge that you've accumulated from just living life. What would be a better oxidizer, water or chlorine? It should be obvious. Hopefully it is. Nobody knows the answer? I'll be surprised. What would you rather bleach your, let's say you want to bleach something, bleach oxidizer. You're going to bleach it with water. You know, let's say you're going to bleach your t-shirt. You're going to bleach your t-shirt with water or with chlorine? No, with chlorine. So it's obvious. We don't need the chart for this. This is totally obvious. Water is weaker, chlorine stronger. As far as reducing agents go, you know, which is easier to burn, hydrogen gas or chloride ions? Well, you know, I tried to catch salt on fire, it didn't. And so this is going to be weaker, but hydrogen is easily caught on fire. So this is going to be stronger. And so the downhill is the reverse. So how do we make this go uphill? How you make this go uphill is by electricity. We have to use electric power to make this go uphill, you know, because there should be no reaction here. And so the way that this happens is it's forced uphill by electrolysis here. So we start here at low energy and go up here at high energy using electrolysis or electricity or electrical power to drive it uphill, because normally it doesn't want to go uphill, it wants to go downhill, right? Well, this is the topic of the last chapter, but there's a lot of chemical reactions in this chapter, so we'll look at them. All right, so the type of question that this chapter asks and answers is, how many kilograms of sodium chloride are needed to manufacture a specific quantity of chlorine? So let's say I wanted 100 kilograms of chlorine. How many kilograms of sodium chloride would I need for that? And it's not 100 kilograms. And so those are the types of questions we can answer in stoichiometry. Stoichiometry is very central to chemistry. Stoichiometry calculations are crucial in chemistry. And so this is a huge topic in chemistry. We want to be able to predict how much we're going to need. Well, it's the same thing. It's a huge topic in everything. Like if you're baking cookies, stoichiometry is incredibly important. Because if you get the stoichiometry wrong, you might have too much sugar in there or not enough chocolate chips or whatever, you got to get the stoichiometry right. And so that's all this is just figuring out which quantities, how much of each do we need or how much of each we're going to make. Okay, let's go on to the next slide. Clear these. Sure. So when we do stoichiometry, we need things that show quantity relationships, chemical formulas. For example, ammonia. Ammonia has 3 hydrogens for every nitrogen. That's stoichiometry right there. So let's say if I have 20 ammonia molecules, how many hydrogens do I have? I'd have 20 times 3, 60 hydrogen atoms, So we need a formula or a balanced chemical equation, So for example, in this balanced chemical equation, this is redox as well. This is redox, but this would be an example of skeleton redox, here, more so, skeleton redox, because ammonia doesn't occur on the chart. And so first off, we need a balanced chemical equation. Well, it depends on how much you burn the ammonia. Here we're burning the ammonia. Ammonia is what we call electron rich, It's electron rich because of the nitrogen, Hydrogen, using our oxidation state rules, hydrogen gets assigned first at +1. And that leaves ammonia at -3. And so we call that pretty rich because ammonia, the nitrogen in ammonia, nitrogen varies from -3 to +5. And so it's on the rich end of the spectrum. This oxygen is 0. And we call 0 poor for oxygen because, we call it poor for oxygen because oxygen would like to be -2. And so, 0 is okay. It's air, but, in geology, you learn that the atmosphere is a very oxidizing atmosphere, The oxidizing atmosphere means that things like iron rust, we get a lot of corrosion. Boats, iron ships rust, it's a constant worry. It's a constant worry because we have this reactive oxygen that's around all the time. We don't notice it because we're just used to living in a very oxidative environment, but there are things, that don't like it. And that would be like iron and other things that are corroded easily by this oxidative environment. So this is why we say oxygen is poor. You might not think it's poor, it's 0, so it should be happy. It should be happy with itself, but it isn't. It wants to be -2. This nitrogen, -3 is what nitrogen wants. Just like oxygen wants to be -2, nitrogen wants to be -3, but nitrogen has a harder time holding on to 3 electrons. And so oxidizers can come in and steal those electrons. It has a harder time because the more electrons you have, the harder it is to hold on to them, that's the situation. Or the bigger you are, you know, like oxygen loves to be -2, but sulfur, you know, sulfur at -2, sulfur is a lot bigger atom. And so, yeah, you go, well, shouldn't sulfur be very happy at -2? Well, no, sulfur is considered rich at -2 because it's so big, oxidizers can come in and steal electrons easily. You know, this is why, you know, sulfur in the -2 is a good reducing agent. You know, this is why in in acetylcysteine, you know, the S, that S is a -2 oxidation state. That S is a good reducer, you know. It's a good reducer because it just doesn't hold on to the electrons as tightly as O2 minus. You know, H2O is not a good reducer. Is this oxygen holds on to those electrons very tightly. And so, you know, I was talking about, you know, chemistry is a mix. Chemistry is a mix of theoretical stuff. So the theoretical stuff would be like, okay, how do you calculate these numbers? But there's also this memorization aspect, and the memorization aspect is, you know, you have to memorize these things. You know, is a -3 rich? Is it poor? Or is it just right? You know, is a 0? Well, it depends on what element you're looking at. Is a +1 poor? Well, it's poor for some. You know, if this were on chlorine, that chlorine would be very unhappy. In fact, bleach is chlorine in the +1 oxidation state, and it's very unhappy. You know, bleach is quite reactive. You know? Whereas a -2 on oxygen, wow, that's happy, but a -2 on sulfur, well, that's rich, you know. And so these little things you have to memorize so that you have some framework for understanding the numbers. Otherwise, it's very hard to interpret. There's no simple way. This is why, you know, a lot of people are talking about, well, you know, machines and AI, you know, machines and AI, yeah, that's going to replace people. That's going to replace the people who can only do calculations, you know, who just take a number and plug it in for X, take another number, plug it in for Y, and then calculate X times Y. You know, that can be replaced by machine or computer. But there are certain things that can't really be replaced because, you know, this requires a higher level, I think, than AI is at this time, you know, and that is this kind of interpretation of these numbers. And so if all you can do is calculate the numbers and you can't interpret it, then you're a good candidate for being replaced by a computer or machine. And to keep, you know, to keep, you know, the full use of your potential, you got to do some memorization like this so you can make more nuanced predictions and more nuanced explanations of things that are happening with this, you know. And so a lot of people say, no, I can just Google it. Well, if you can Google everything, then there's no need, you know, there's no need for your expertise. There's no need for your knowledge. Because if all you can do is Google something, then, you know, they can hire an elementary school or, you know, in other words, think about it, you know, think about it, because I hear people say this all the time, but, you know, what are they saying? Do they want to be replaced by a computer? You know, I don't know. Okay, so let's continue on here. Is it break time? Yeah, sorry, it's break time. So I missed that on the chat. Okay, let's take a 15-minute break. Oh, I went over, well over. So we'll start at 1, okay? So 15-minute break, start at 1. Okay, let me, I'm gonna stop the recording. Hopefully, won't forget.